Welcome to Strength of Materials N5. Today's presentation is on simple bending of beams. Before I begin, I will say that it is important for you to understand how to draw a shear force diagram and a bending moment diagram. Okay, this is what you learned in engineering science N4. So for strength of materials, we just assume that you already have that knowledge. So if you do not remember how to draw a shear force diagram, or you are not very comfortable with that, or how to draw a bending moment diagram, I will advise you to go and watch my video. I made a video for engineering science N4 where I explain in details how to draw a shear force diagram and how to draw a bending moment diagram. So you can just go and refresh your memory on that, because in this presentation I am not going to devote time trying to explain to you how to do that. I am just going to assume that you already know how to do that. So if you do not, I will advise you to go and look on this channel. There is a video on drawing shear force diagrams and bending moment diagrams, and you can just learn from that video. Then you can come and watch this one. Having said that, I will also say this is one of the modules for Strength N5 that students find challenging, so it can benefit you to watch this video at least 2 or 3 times just to make sure that you understand everything. Okay, so let's begin. So first, let us talk about loadings. But before we do that, I will introduce to you the general bending equation that we have, and this is what you see on the screen. Okay, so basically your moment of resistance, or your bending moment, divided by the area moment of inertia, or the second moment of area, okay, is equal to the bending stress divided by y. Now this y that you see here is the distance from the neutral axis. Okay, sometimes they will ask you to find the stresses at a certain distance from the neutral axis, and so that is what y is. Y is the distance from the neutral axis, and this is also equal to the Young's modulus divided by the radius of curvature, which is r. Okay, so this equation here is what we refer to as the general bending equation, and there are many equations that you can derive from these. For instance, you could find an expression for the stress in terms of the moment, the second moment of area, and y. Okay, so you could rewrite stress is equal to my over I, because m over I is equal to stress over y. Okay, so but this that you see here is the general bending equation. And also I need to introduce to you the equation for the section modulus. The section modulus is given by the moment of resistance divided by the bending stress, and that's also equal to the second moment of area divided by y. Okay, so z that you see here is referred to as the section modulus. So in some of the questions, they will ask you to find the section modulus. You will just need to remember this equation, and you will use the format that is more convenient. Now, let us look at the radius of gyration, which is k. And k is equal to the square root of I over a. I here is the second moment of area, or if you want, you can also call it the area moment of inertia. And you need to divide that by the cross-section area of the beam. Then when you take the square root of all that, that is what gives you the radius of gyration. So it is possible that you could also get a question where they ask you to calculate the radius of gyration, so you will just remember this formula. Now let us look at the loadings. The first type of loadings is when you're dealing with cantilevers. What is a cantilever beam? When we say that a beam is a cantilever, it means that it is a beam that is planted in a wall. So on the one end of the beam, you have a fixed support, and then it is free on the other end. That is what we refer to as a cantilever. So it is a situation like this. As you can see, we have a beam here. The length of the beam is L, and this beam is planted inside of a wall. Okay, so here it's a fixed support, but here it is free. That is what we refer to as a cantilever. So now we will look at the moment of resistance that you have for different types of loadings that you get on a cantilever beam. So let's say that you have a force W that is applied at the free end of the beam. Then what will the moment of resistance be? In this case, it will be equal to the magnitude of the force W multiplied by the length of the beam. So this is how you will get the moment of resistance when you have a cantilever beam with a load, a point load applied at the free end. So you just need to multiply the force by the length of the beam. You can have a different situation where you have a cantilever beam, but this time you have a distributed load that is applied over the length of the beam. Now, the magnitude of the distributed load is small w, okay? And so, how do you get the moment of resistance in this case? It's simple. It's going to be equal to small w multiplied by the length of the beam squared, and all of that divided by 2. Now, let's say you have a situation where you again have a cantilever beam and you have a point load at the free end, but that's not the only load that you have. You have also a distributed load over the length of the beam. Now, as you can see, if you look at this situation here, it is a combination of this situation and that situation. So how will you get the moment of resistance for this situation? You just combine these two, so you sum them up. So the moment of resistance will be equal to WL, which is this situation, plus small WL squared over 2, which is that situation here. So when you have a combination of loadings, the moment of resistance is equal to the sum of the moments of resistance of those two separate situations. I hope I am making myself clear. Okay, so as you can see, I need to repeat this because usually in your question, they will give you some sort of a combination of loadings, and it's going to be up to you to remember that this is that scenario plus this scenario. And then you can then add the moments of resistances to get the total moment of resistance for that particular situation. Okay, so as you can see, what we have here is a combination of this scenario here and that scenario there. Okay, you have a point load and you have a distributed load over the length of the beam. So since the two are combined, then the total moment of resistance must be the sum of each of the moments of resistance. Okay, I hope this is making sense. Now, we don't just have cantilevers, but you also have simply supported beams. Now, simply supported beams are beams that are resting on simple supports, okay? So, if you look at this here, you can see this is a beam and the length of the beam is L, and it is resting on a support on the far right and then on another support on the far left. So these supports are creating a reaction, and then this beam is loaded with a force W, okay? And so this is a situation of a simple support with a point load acting in the middle of the beam. When you have a situation like that, then the moment of resistance is given by this equation, okay? So it's going to be equal to the magnitude of the force multiplied by the length of the beam, and all of that divided by 4. And you can also have a situation where you have a simply supported beam with a distributed load acting over the length of the beam. And so in this case, if we want to find the moment of resistance, it's going to be equal to small w, which is the magnitude of the distributed load, multiplied by the length squared, and all of that divided by 8. Now, what if you have a situation like this? As you can see here, we have a point load acting in the middle of the beam, and that is coupled with a distributed load acting over the full length of the beam. And so if that is the case, you need to be wise enough to recognize that this here is a combination of that and of this. So therefore, the moment of resistance will be the sum of the moments of resistance of each scenario. Okay, so in this case, therefore, the moment of resistance will be equal to W multiplied by L over 4, that is big W, which is the magnitude of the point load, plus small w, which is the magnitude of the distributed load, multiplied by the length of the beam squared, and all of that divided by 8. And as you can see here, we just summed this and that, okay, because this case here is a combination of this and of that, okay. Now, I need to point out to you that this case that you have here is a case where the point load is acting exactly at the middle of the length of the beam, okay? That is what we have here. So when we have a point load acting exactly at the middle of the length of the beam, then the moment of resistance or the bending moment is given by this equation here. But we do know that we can also have a situation where we have a point load, but it's not acting exactly in the middle of the length of the beam. So when that is the case, how then do you get the moment of resistance? It's not as difficult as it sounds. So this is a situation that you see here, the situation that you see here, and as you can see, we have a simply supported beam of length L, but this time the point load is not acting in the middle of the length of the beam. Okay, it is acting at a distance A from the left end and at a distance B from the right end, and A and B are not equal. Okay, so as you can see here, this point load is not acting in the middle of the length of the beam. So how will you get the moment of resistance for a situation like that? It is given by this equation. Okay, so the moment of resistance or the bending moment, it's the same thing, is going to be equal to the magnitude of the point load multiplied by this length A in meters multiplied by that length B in meters, and all of that divided by the length of the beam, which is also in meters, okay, SI units. And so this is how you will get the moment of resistance when you have a point load that is not acting in the middle of the beam. If it is acting exactly in the middle of the beam, then this is how you will get the moment of resistance, okay, using that equation. And so, of course, you can also combine a situation like this with a situation like that, okay, and that's fine, okay. You just need to read the question carefully. If you have a situation where you have a point load that is not acting in the middle of the length of the beam, and on top of that you have a distributed load that is acting over the full length of the beam, then the total moment of resistance will therefore be that plus this, okay. I hope it is making sense. So here I was just presenting to you the general situations that you will encounter. So now when you get a question, you need to be wise enough to know what needs to be combined with what for you to actually get the total moment of resistance. Now let us speak about the centroids.